Today we are going to talk about commonly used negative feedback op-amp circuits. And we are going to use the ideal op-amp model in order to analyze these circuits. So before we apply these ideal op-amp rules, I want to go over them again just very briefly here. We talked about them at the very end of our last class meeting, but just to make sure that everybody's catching what I'm throwing. Anytime that we see an op-amp in our circuit and we have negative feedback, goodness gracious. So that would be a situation like this. Here's my op-amp, my inverting input terminal, my non-inverting input terminal. So if I have some feedback path connecting my inverting input to my output like so, I have a negative feedback system. I've just drawn some ellipses here. So this would be V plus and this would be V minus to indicate that we might see further circuit elements and all of that kind of good stuff going on. I've also specifically used generic two-port or two-terminal circuit elements here, so not specifically resistors, capacitors, or inductors, to take into account that we may be using different types of components to establish these feedback and biasing networks. But anyway, so anytime we have a system where we've got a connection from our output node back to our inverting input node, we have a negative feedback amplifier system. And the two rules that we're going to use to analyze these circuits are as follows. So no current can flow into or out of the input terminals of the op-amp. As we saw in our last class meeting, this is because the input resistance of the op-amp is so large that in an ideal case, we typically treat it as an open circuit, right? So that means that this current right here, which I'm going to label as, let me get rid of this thing, I minus would be equal to 0 amps. And similarly, this current right here, which I'm going to label as I plus, would also be 0 amps. Our second ideal op-amp rule, this comes from our voltage constraint relationship that we developed at the end of our last class meeting, where for an ideal op-amp, we have an infinite open loop voltage gain, which effectively forces our differential voltage to be 0 in a closed loop system with negative feedback. So we'll have the relationship, there can be no voltage difference between the input terminals. And so I would typically represent that as the voltage V plus must be equal to the voltage V minus. So, or the nodal voltage at the non-inverting input node must be identical to the nodal voltage at the inverting input node. And we might choose to represent that on our schematic diagram by saying that there is no voltage drop between those two terminals, okay? So those are our ideal op-amp rules. And as I mentioned, they're going to be part of the analysis that we're doing as we look at all of these different commonly used circuits. So we're going to start with the most commonly used circuit. And so that is going to be it's called the inverting amplifier. So in an inverting amplifier circuit, and we'll do this the most generic way possible, we might have something like this, where I'm going to have a feedback resistance connecting my non-inverting input node, excuse me, my inverting input node to my output node like so. I'm going to call this resistance RF. I'm going to have some resistance here that I'm just going to call R1 for lack of a better term here. And I would apply my input signal to the left hand of this leg R1. I'm going to simply ground my non-inverting input node like so. And for right now, I'm going to just take my output voltage as the open circuit voltage, so measured between that node on the op amp and ground. A couple of quick things here. So I'm probably not going to bother writing these every time. We are just going to assume that our op amp is sufficiently powered to be behaving correctly. So VCC plus and VCC minus will just have whatever voltage is necessary to make this circuit work. And I may neglect to even draw those power supply terminals here moving forward. So we will always assume that our op amp is on and functioning properly. Okay. So for this particular circuit, if I apply op amp rule number 1, so I'm just going to indicate here that this current is 0 amps and this current is 0 amps. I can see, I hope pretty easily, that the voltage present at my non-inverting input node V plus is going to be 0 volts. And from that, the nodal voltage at my inverting input node is also going to be 0 volts, right? Applying Kirchhoff's current law at my inverting input node means I'm going to add this current flowing to the left through R1 plus this current flowing to the right through RF together. And so what I'm going to wind up getting is, so this will just be KCL at V minus. And what I'll wind up getting is 0 volts minus Vn. So I'm just going to write this as negative Vn divided by R1 plus my current flowing to the right through RF is 0 minus V out. So I'm just going to write that as negative V out over RF is equal to 0. And I can rearrange this slightly and find that our output voltage is simply going to be negative RF over R1 times Vn. And from here, I could say that my closed loop voltage gain, which is just the ratio of V out over Vn for the system, comes out to be negative RF over R1. So let's talk about a couple of things here. First, the name. So this is an inverting amplifier. This is an inverting negative feedback amplifier. So we've dealt with amplifiers where we applied the input signal on the inverting side before. So the inverting Schmitt trigger, we applied the input signal on the inverting input side of the amplifier. for our inverting comparator, we had our input signal applied on the inverting input side of the op amp as well. All of that inverting stuff really means is that if I apply a positive polarity input signal, I'm going to get a negative polarity output signal. And we can see that very specifically here because our closed loop voltage gain is negative, right? Negative RF over R1 will always be a negative quantity because our feedback resistor and our R1 resistor are always going to be positive resistances. Josh.
So like for a voltage input, like in the past, like you wrote it to where it's your voltage signal is a function of time. Is that basically the same thing, but just a different limitation or no?
So Vn can be a time varying function here, and if Vn is a time varying function, then V out would be a time varying function as well. Did that answer your question? Okay. So I just labeled it as Vn, not specifying here. We can definitely use an inverting amplifier like this to boost the level of a DC signal, but that is the most boring application that we could have for a negative feedback op amp, is just bumping up DC signals. That is possible. It's just there are other ways to do it. I'm not saying that they're necessarily better ways, but op amps, particularly negative feedback op amps, are used for what's called analog signal processing. That is literally what they were designed to do. And so that would typically be time varying signals that are boosting. So in this particular case with our inverting amplifier, we can make our output signal larger than our input signal by having RF being larger than R1. Or we can actually use it to attenuate signals or make them smaller than the input, right? So if RF is smaller than R1, then our output signal would be smaller than our input signal. So we have a lot of versatility here because we can make our output both larger than or smaller than our input signal in magnitude, but we are always going to get a signal of the opposite polarity. So if we put a positive voltage signal in, we get a negative voltage signal out. If we put a negative voltage signal in, we get a positive voltage signal out. So essentially our input signal and our output signals will always be exactly 180 degrees out of phase. So when one is rising, the other is decreasing and vice versa, okay? So this is the first amplifier. Before we move on from this one, I want to show you a couple of things here, okay? So the first of which is, in some cases, and I'm going to do these in pink because they're kind of optional from a circuit analysis standpoint, but important from a practical implementation standpoint. So we might see a resistor connected to the non-inverting input terminal here, okay? I'm going to call this guy R sub B, okay? So the purpose of this resistor is to mitigate what are called input offset currents, okay? So essentially, we can have a small amount of current leakage going into some particular op amp models that we need to be able to limit or negate. And that's what that resistor RB does there. From a circuit analysis perspective, that resistor RB may not as well be there because we are saying that there is no current flowing through it. Since there's no current flowing through it, there's no voltage drop across it. And so it's essentially being treated as a short circuit in our analysis. So it's there for a practical purpose, but from the analysis side of things, it's really not doing much. We might also see systems where we have some load resistance RL here. Does the presence of the load resistor RL in any way, shape, or form change the input output or transfer function relationship for this op amp? It does not, okay? So in an ideal op amp, the presence of a load resistor will not impact our voltage gain or anything like that. So we can, for all intents and purposes, ignore that, okay? Any questions about this guy before we move on to the next one? All right, so the next most commonly used amplifier is going to be the non-inverting amplifier, and it is going to look incredibly similar. So I've got my op amp here. Applying negative feedback across the top again. Like so. Got my resistor R1 connected between the inverting input terminal, and in this case, instead of having it connected between the inverting input terminal and my input signal, I'm going to connect it between my inverting input terminal and ground, like so. So here's my resistor R1, and then over here on the non-inverting input side is where I'm actually going to apply my input signal, and then I'll measure V out over here with respect to ground at the output terminal of the op amp. Okay.
Question.
Yes, sir.
Will RF always be connected to our non-inverting or our inverting side of the op amp?
Yes. For a so all of the circuits that we're dealing with today specifically are going to have negative feedback, so it will always be between the inverting input terminal and the output terminal, because that is what means we have negative feedback in an op amp circuit. So just for what it's worth, what we did prior to, so I guess last Wednesday's class meeting, all of those circuits had some sort of conductive path, usually in the form of a resistor, between the non-inverting input terminal and the output terminal, and we considered all of those to be positive feedback systems. Okay, so applying our ideal op amp rules, once again, we're going to have 0 amps flowing here and here. We can see very easily that the voltage present at our non-inverting input terminal is just Vn, which means the voltage present at our inverting input terminal is also going to be Vn. From there, we can apply Kirchhoff's current law at our non-inverting input node yet again. And what we'll get when we apply KCL in this way is Vn divided by R1 plus Vn minus V out divided by RF is equal to 0. And that can be easily rearranged to V out is equal to 1 plus RF over R1 times our input signal, and therefore our closed loop voltage gain, sorry, that should be AVCL, got my subscripts mixed up, is going to be simply 1 plus RF over R1. This type of circuit is exactly what we analyzed in our last class meeting, where I had a feedback resistance of 10 kiloohms and an R1 value of 5 kiloohms. And so we wound up getting a gain of 1 plus 10 over 5 is 3, right? So we've already seen this guy before, okay? So a couple of things that I want to point out about this guy. First, the input signal is applied on the non-inverting side, which is why we have a non-inverting amplifier. And so that means that our output signal and our input signal are going to be in phase. So there is no phase shift between them, okay? The lowest gain that our non-inverting amplifier configuration could ever achieve is exactly 1. So we can only use this type of amplifier to either keep our signal the same or boost it, okay? When we keep our signal the same, so this is going to be kind of a special case thing, I'll just write it under here. So when RF is much, much smaller than R1, we have a unity gain buffer amplifier, okay, where our closed loop voltage gain is going to be approximately equal to 1. That's what unity gain means, is a closed loop voltage gain of 1, okay? So it may seem kind of odd to have an amplifier whose gain is 1 or as close to 1 as we can possibly make it. But this is actually a very, very common amplifier that is used in a lot of different situations. Predominantly, we would use a unity gain buffer amplifier in a situation to where whatever signal that we are trying to process can generate a reasonable amount of voltage, but can't really generate current or anything like that. So we would use a unity gain buffer essentially to be able to use those power supply voltages to inject current into our system that could be used to do something else. So you'll see unity gain buffers used a whole lot in instrumentation amplifiers and things like that. The input of a particular sensor might be ran through a unity gain buffer before it's ran through an actual amplification stage. And a lot of biomedical applications and chemical process applications and things like that. So the unity gain buffer is a way for us to preserve our input signal while drawing power in from elsewhere to do other things, okay? So how many, if any of you all, are familiar with piezoelectric crystals? A couple of you guys are raising your hand saying yes. So a piezoelectric crystal is a type of material that when it undergoes mechanical deformation, it generates a voltage, right? So we could use a piezoelectric crystal as a type of sensor to see whether or not something has taken an impact or something like that, right? If we deform that crystal, it generates a voltage. However, the voltage that's generated by a piezoelectric crystal can be quite large. It's dependent on the rate of change of the deformation, but the current that's generated by such a sensor is actually really, really low. So if we wanted to use a piezoelectric crystal as a sensor, we would probably have the output of that sensor go through one of these unity gain buffers so that we get a really good snapshot of what the voltage is doing. And then we would use the unity gain buffer itself to supply current to subsequent stages as is necessary. So trying to just clue you guys in on where these guys are applied. Okay. Yes.
So, like kind of bringing it back a little bit, when gain is applied to the inverting side, did you say that is what causes that, 180-degree phase shift?
Yeah. So when we look at a differencing amplifier here in a moment, we'll see that very definitively. In fact, so well, I'll show it to you in a couple minutes. Okay. So we've talked about the inverting amplifier. Now we've talked about the non-inverting amplifier. Let's do summing amplifiers first, and then we'll do differencing amplifiers. Okay. There's not enough room down here, so I'm going to scroll to the next page. So this next guy that we're going to look at is the weighted inverting summer. So this is how one of a couple of different ways that we can perform the addition mathematical operation using an op-amp. So operational amplifiers were literally developed in order to do, as I mentioned earlier, analog signal processing. And what I mean by that is performing math on signals, adding them together, taking the difference of them, integrating them, differentiating them, etc. Okay. So this guy right here is how one way that addition can be performed using op-amps. So if I have my op amp here, and once again, I'm going to have negative feedback. So this is my resistor R sub F. What I'm going to do over here is a little bit different than what I did for the last example. So I'm going to have a resistor R1 here, and it's going to have a corresponding input V1. And then I might have a resistor R2 that has a corresponding input V2. And I might have a resistor R3 that has a corresponding input V3, and so on and so forth. So if I connect these input signals on the inverting input side, I can actually have essentially an infinite number of inputs and everything will work out pretty okay. That we can do a non-inverting summer amplifier, but the math gets real gross real quick because each individual input scaling factor is just going to kind of go bananas, not particularly well behaved. So usually addition is performed using the inverting style of summer like this one. I'm going to connect my non-inverting input terminal to ground like so. And I'm going to take my output voltage here at the output terminal, and it'll be measured with respect to ground. So applying my ideal op amp rules, once again, 0 amps flowing into the input terminals of my op amp, I can see very easily that the voltage present at the non-inverting input terminal is 0 volts, which means the voltage present at the inverting input terminal is also 0 volts. And now I'm going to apply KCL at my inverting input node. So that's adding this current plus this current plus this current plus this current together, setting them equal to 0. So my KCL equation should look like negative V1 over R1 minus V2 over R2 minus V3 over R3 minus V out over RF is equal to 0. And then I can rearrange that guy and find that V out is going to be equal to negative RF times V1 over R1 plus V2 over R2 plus V3 over R3, and so on and so forth. Okay. So we can't really define a closed loop voltage gain for this system because we have a combination of outputs, but we can hopefully very easily see that if we were trying to see the voltage gain for input signal V1, it would just be negative RF over R1. For input signal V2, it would be negative RF over R2, etc. So each of these three input signals, V1, V2, and V3, can be scaled by a different amount depending on what resistor value we place between that input signal itself and the inverting input node, okay? So that's why we have a weighted inverting summer, because each individual input signal is weighted by some different amount. When R1 is equal to R2 is equal to R3 is equal to what I'm just going to call R, all of our signals would be scaled by the same amount. And so we'll no longer have a weighted inverting summer. We'll just have an inverting summer. Okay. So that case would look something like V out is equal to negative RF over R times the sum of V1 plus V2 plus V3. I'm going to put a note here. This is just an inverting summer. All right. Does anybody have any questions about this analysis or the output relationship or anything like that? Yes, sir.
This one of the op-amps is typically used in like a TI-36X or the more complicated calculus.
So your calculators will definitely have some op amps in them. But most of what's going on in your calculator would be what I would call digital signal processing. So you're just taking in probably binary or hexadecimal input signals, representative of different numbers and things like that, and then you're processing those. So something like this, do you have a bathroom scale?
Yeah.
Is it digital or analog?
Digital.
That's literally what's used to calculate your weight. So you'll have, let me draw a crappy little picture here. So my bathroom scale at home is a square dealio. And then it's got a place that it tells me to put my feet. So one oval over here is for my left foot. This oval over here is roughly for my right foot. And so there is a load cell connected here, 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 and here. So each of these load cells converts effectively how much pressure I'm putting on them because of how much I weigh into an electrical signal. So it takes in force or pressure and it outputs a voltage. Well, then an op amp is actually used to add all of those voltages together, and that will give me an indication of what my weight is, okay? So the load cell itself, if you look at the data sheet, it's going to tell you, oh, it might generate, 1 millivolt for every kilogram or something like that. And we could use the ratio of resistances to convert that output of the load cell from millivolts per kilogram into essentially volts per pound or something like that by scaling it in that way. So if you drive across the state lines, the huge weigh stations are just using a larger version of this where they're using nickel strain gauges essentially as the load cells that deform under the weight of a 18-wheeler, but it's the same exact principle. So, yeah. All right. Any other questions about this guy before we move along? Okay. So answering Josh's question about the inverting and non-inverting inputs, we're going to look at what's called a differencing amplifier. And I'm going to analyze this circuit a little bit differently than I've done the previous examples, just to illustrate what I was talking about the inverting input gives us an output that is 180 degrees out of phase and so on and so forth, right? So our amplifier circuit is going to look something like this. And I'm going to change it up ever so slightly from back-end circuits one in a different way. I'm going to call this resistor right here R2. And I'm going to call this resistor right here R1. And I'm going to call this input signal V1. Okay. Here's my output voltage. Now on the non-inverting input side, I'm going to have another resistor network. Okay. So this guy is going to be R2. This guy is going to be R1. And this is going to be my input signal V2. Okay. So I want us to use superposition to figure out what's going on here, right? If you want to see this circuit analyzed the way that we've done the previous ones, you can watch my Circuits 1 videos from the last couple of quarters, but I'm just trying to illustrate something a little bit different here, right? So how many of you guys remember superposition principle? Anybody? Nikolai, you raised your hand. What is it? Ballpark it.
Turn one thing off, see how one reacts when it's off.
Yep.
The other one.
Exactly right. So let's start by having V1 on. And V2 off. So if I essentially, I'm going to wind up erasing this here in a moment, but if I were to ground this guy so that V2 was off, what kind of amplifier would I have?
Just inverting.
Just a simple inverting amplifier, right? So we could see that V out prime is going to be negative R2 over R1 times V1. Okay. So my input signal applied on the inverting side is going to 100% of the time give me an output that is 180 degrees out of phase because of that negative sign out in front there, right? Now, let's look at what happens if we analyze the circuit with V1 off and V2 on, okay? So essentially, I'm grounding this guy up here, okay? So I need to look at something here real quick that's just going to help me analyze what's going on here. Sorry about that, Connor. So recognizing that no current can flow into or out of the input terminals of my op amp, that means that my voltage source V2 is just going to see those two resistors R1 and R2 in series, essentially, right? So how would I find the voltage present at this particular node? Voltage division, okay? So what would that look like? Let me give myself enough room here, actually. So V2 multiplied by R2 over R1 plus R2, okay? So if I treat that as this whole effective network as my source, what kind of amplifier do I have now? A non-inverting amplifier, right? So I would see that, let me do it in this color, I guess. V out double prime would be positive V2 times R2 over R1 plus R2, so that's my input signal, times 1 plus R2 over R1. Okay. Well, I'm going to do something maybe a little odd here. I'm going to change that 1 into R1 over R1. So that I would have R1 plus R2 all over R1. Can we agree that 1 plus R2 over R1 is the same thing as R1 plus R2 all over R1? We can observe that that numerator cancels that denominator, and I'm left with a factor of V2 times positive R2 over R1. Okay. So what happens when I add these results together? Oh, and just for what it's worth, the polarity of the output signal here is of the same polarity as the input signal because that input was applied on the non-inverting side, right? So there is no negative sign, there's an implied plus sign, okay? So using superposition, I know that my output voltage should just be V out single prime plus V out double prime, right? That's just going to look like a factor of R2 over R1 multiplied by V2 minus V1, which is just the difference of the input signals. Okay. So this is a differencing amplifier because it gives me a scaled representation of the difference of those two inputs. So it's taking the difference, V2 minus V1, and then scaling it by R2 over R1, where those resistors R2 need to be matched to each other perfectly, and those resistors R1 need to be matched to each other perfectly. Otherwise, I'm going to get slightly different scaling on V2 and V1. Okay. So any questions about this guy? And hopefully we can see pretty easily input signal on the inverting side contributes to the negative sign. Input signal on the non-inverting side converts to what's going on with a plus sign over here. Okay. So we've scaled our input signals. We've added input signals together. We've taken the difference of input signals. So now let's do calculus with op amps. Okay. So as a quick reminder over here on the right, so I'm going to choose to implement these circuits using capacitors and resistors. We could implement these circuits using inductors and resistors. The reason why typically in practice capacitors are used is because the tolerance of a capacitor is usually much smaller than the tolerance of an inductor. Meaning if you nominally purchase a 47 nanofarad capacitor, it's going to be pretty close to 47 nanofarads. Whereas if you were to get a 1 millihenry inductor, it's not going to be as close to 1 millihenry as the capacitor was to its nominal value. So in order to use quote unquote cheap circuit components, capacitors are the better way to implement these guys. Okay, so I've explained why I'm using capacitors specifically. So let's remind ourselves of capacitor relationships. So hopefully we remember that the current flowing through a capacitor, IC of t, is C times the derivative of the voltage drop across the capacitor with respect to time. And we could rearrange this guy and find that the voltage drop across a capacitor is going to be equal to 1 over C times the integral of the current flowing through the capacitor, IC t prime dt prime, where I've integrated from negative infinity to t, the time that we're interested in, and I'm choosing to use the negative infinity representation of this integral just so that I don't have to bother with what's going on with the initial conditions on the energy stored in the capacitor. So this is just going to make the math slightly easier. Okay. So let's start with a situation, and I'm going to go out on a limb here, and I'm going to say that I'm talking about the differentiating amplifier first. And if it turns out that I accidentally have it backwards, I'll wind up erasing that and saying it's an integrating amplifier because I can never remember which one is which. But I'm 90-ish% sure that I'm doing this correctly. So I'm going to put some resistance R in a feedback position across my amplifier like so. Let's just call it R. Here is my output terminal, and I'm going to explicitly put V out of T here because this circuit will not work for DC circuits because in a DC circuit, my capacitor is just going to look like an open circuit and it's not really going to do anything. And then over here, I'm going to put my capacitor C. Here's my input signal Vn as a function of time, and I'm grounding my non-inverting input node like so. So before we get into our analysis, I am explicitly going to say that, let me use this hot pink thing here. The voltage drop across my capacitor, Vc of t, is going to have positive polarity on the left, and the current flowing through my capacitor, Ic of t, is flowing into the positive polarity terminal. Okay. So now we can get into the analysis here. Okay. So I can observe that there is no current flowing into or out of my input terminals due to the ideal op-amp rule number 1. Ideal op-amp rule number 2 tells me that since the voltage here is 0 volts, the voltage here must also be 0 volts. And now I'm going to apply KCL at my inverting input terminal like I've been doing. I'm going to do it ever so slightly differently. In every other example, I had currents flowing out add together to equal 0. This time I'm going to do current flowing in is equal to current flowing out. So that's going to give me IC of t is equal to 0 volts minus V out. So negative V out divided by R, right? Well, I could rearrange this guy and say that V out as a function of time is then just negative R times IC. And because I know the current flowing through my capacitor is related to C times the derivative of the voltage drop across my capacitor, this is going to become negative RC times the derivative of VC with respect to time. And so all I have left to do now is figure out how VC and VN are related to each other. Somebody who didn't take me for circuits 1 and therefore doesn't already know what the answer to this is, tell me what's up. So how are VC and VN related? They are the same, yeah. So that VN is a shorthand notation for a voltage source where the positive polarity terminal of VN is applied at that node and the negative polarity terminal of VN is at ground, right? Well, VC has the positive polarity terminal at the same place that VN does, and the negative polarity terminal of VC is at the inverting input terminal, which is at a virtual ground because the non-inverting input terminal is physically grounded out. So VC and VN are exactly the same quantity. And so we get negative RC times the derivative of VN with respect to time. So this is indeed a differentiating amplifier, okay? So this is what this circuit is called in a analog signal processing context. But this circuit is also an example of an active high pass filter in communication systems. It's a differentiator block in control systems, all related to essentially the exact same circuit, just plays slightly different roles in the different systems that you're going to see throughout your electrical engineering career. So this guy is rather important. Okay. Before we move on to the integrating amplifier, does anybody have any questions, comments, or concerns? All right. So the last one that we're going to talk about today is our integrating amplifier. And the integrating amplifier is the exact same circuit that we just had, except that the R and the C are switching places. So something akin to this. So my capacitor is in the feedback position now. Here's my resistor R, my input signal Vn of t. I'm once again going to ground my non-inverting input node, and here's my output signal V out of t. I'm going to define the voltage drop across my capacitor once again with positive polarity on the left, and my current flowing into my capacitor IC will be flowing into that positive polarity terminal. So applying our ideal op-amp rules, we can see that we have no current flowing into our input terminals. The voltage present at the non-inverting input terminal is 0 volts, which means the voltage present at the inverting input terminal is also 0 volts. And much like I did in the last problem, I'm going to choose to express my KCL relationship as the current flowing in is equal to the current flowing out. So when I perform KCL here, I'm going to have a current of Vn divided by R is equal to IC, right? So I'm going to hold on to this relationship for a moment, okay? So it's a little bit difficult to relate the current IC to the output voltage V out of T, right? I have things in terms of my input voltage. Now I have to figure out how to get my output voltage into this expression somehow, okay? So instead of trying to relate IC and V out, I want to see if we can relate VC and V out. Does anybody have any thoughts on that one? So we don't need to do anything fancy like that, okay? So let me explain what I mean by that. I'm going to draw something here that makes hopefully things a little bit more obvious, right? So my output voltage is a voltage measured with respect to ground, okay? So notice that the positive polarity terminal of the output voltage is at this node, and the negative polarity terminal of VC is at that same node. Okay? We can also observe that the negative polarity terminal of our output voltage is at ground, and the positive polarity terminal of VC is at ground. So that means that VC and V out are the same voltage, they're just of opposite polarities, right? So we could say that VC is negative V out, and therefore V out is negative VC, and then using this integral based relationship from up here, that would look like negative, my stylus will write, 1 over c times the integral from negative infinity to t of IC of t prime dt prime. And now I can substitute in that relationship for IC that is in terms of Vn, right? I'll do that below here. So I'm going to have negative 1 over c times the integral from negative infinity to t of Vn over R And since R is a constant, I can just pull that outside of the integral, and that leaves me with -1 over RC times the integral from -infinity to t of Vn dt, like so. So this particular configuration, where I have the capacitor in the feedback position, gives me an output that is a scaled version of the integral of the input signal. For what it's worth, this is also a high-pass filter in communication systems, an integrator block in control systems. Both of these guys are an example of phase shifting circuits. So what I mean by that specifically is since if you put a cosine function in and you take the derivative, you get a negative sine function, right? So that's actually giving you a 270 degrees phase shift. If you put a cosine function into the integrator, you get a positive sine as the output. So that's giving you a positive phase shift of 90 degrees. So when you look at some of your different design projects, prompts particularly, these guys can be rather useful, right? So let's say, for example, if I wanted to convert a square wave into a triangular wave, I could use an integrator to do that, because the integral of a constant function is going to look like a line that's increasing at a constant slope. So integrators convert my square waves into triangular waves or sawtooth waves, stuff like that. So anyway. All right, so I think that's enough out of me for today. These are the 6 most commonly used negative feedback op-amp circuits that you can implement with a single op-amp